All right, so we're going to be working on Chapter 5, Lesson 6, working with radical expressions. So, what we're going to learn about is how to simplify a radical expression, how to add, subtract, multiply, and divide radical expressions. So some of the vocabulary to keep in mind is rationalizing the denominator, what are like radical expressions, and what are conjugates. So, how do radical expressions apply to falling objects? So the amount of time t in seconds that it takes for an object to drop d feet is given by t equals the square root of 2d over g, where g equals 32 feet per second squared is the acceleration due to gravity. In this lesson, you will learn how to simplify a radical expression like the radical 2d over g or square root of 2d over g. Simplifying radical expressions. You can use the commutative property in the definition of a square root to find equivalent expressions for the product of radicals, such as radical 3 times radical 5. And you begin by squaring the product. So for example, if I had the square root of 3 times square root of 5 and I squared it, that would be the same as square root of 3 times square root of 5 times square root of 3 times square root of 5, right? I'm multiplying it times itself. Now with the commutative property, I could rearrange it so I can put the radical 3's next to each other and the radical 5's next to each other. And then using the definition of a square root, right? Square root or radical 3 times radical 3 is radical 9, or the square root of 9, or radical 3 squared, which would be 3. And the square root of 5 times square root of 5 would give me 5. So this would allow me to give me 3 times 5, which is 15. So since the square root of 3 times the square root of 5 is greater than 0, that means that it has to be equal to square root of 3 times square root of 5 squared has to equal 15. And square root of 3 times square root of 5 is the principal root of 15. That is, the square root of 3 times the square root of 5 has to equal the square root of 15. This illustrates the following property of radicals. So first property we're going to talk about is the product property. For any real numbers a and b, and any integer where n is greater than 1, if n is even and a and b are both non-negative, then the nth root of a times b is equal to the nth root of a times the nth root of b. And if n is odd, then the nth root of ab is equal to the nth root of a times the nth root of b. And so this product property is showing you that if you have the root and the product of two values, that it's just equal or equivalent to that root of the first product times that root of the second product. So you can always follow these steps to simplify a square root. Factor the radicand into as many squares as possible. Use the product property to isolate perfect squares and simplify each radical. So let's look at an example. So if I look at the square root of a product, right, I can break this apart into squares where possible, right? Well, I know 16 is just 4 squared. I know p to the 8th is actually just p to the 4th squared. And q to the 7th power, I could actually do q to the 3rd squared, because that's actually q to the 6th q, right? So this would actually be equivalent to q to the 7th. But if you notice, I have a perfect square right there. And why would I want to do a perfect square? Because now I can break them apart, right? I can, using the product property for radicals here, I know that if all of these things under the radical are multiplied together, I can actually just multiply them with their own separate radicals. So if I do the square root of 4 squared, that's just 4. If I do the square root of p to the 4th squared, that's just p to the 4th. If I do the square root of q to the 3rd squared, that's just q to the 3rd. And the main reason why it's got the absolute value, we went over this in 5-5, where because I have an even root and my even root has an odd exponent, this could potentially be positive or negative, but I need it to be positive because I need this value in here to be positive, because if it's not, then I couldn't do the square root of it. And then the square root of q, well, that can't be simplified because I don't know what q is, and that's not a perfect square. So that remains under the radical. And so this would be my simplified answer there. So, however, for the square root of 16p to the 8th q7 to be defined, this must be non-negative, right? This has to be a non-negative. And if that is true, then q must also be non-negative. And since it's raised to an odd power, thus the absolute value is unnecessary. And so really, I could just write the answer without the absolute value there. So let's look at radicals that involve division. If you look at these, you can see that there is a quotient property that is similar to the product property. So consider 49 over 9. The radicand is a perfect square. So if I have the square root of 49 over 9, that's equal to the square root of 7 squared and 3 squared, right? Or 7/3. So notice that 7 over 3 is equal to the square root of 49 over the square root of 9, right? Because both of those will be equal to each other. So this suggests the following property, which is our next one, which is the quotient property. So if I have the nth root of a over b, that's equal to the nth root of a over the nth root of b. Again, allows us to kind of break up or split up the root. So again, if I had the square root of 27 over the square root of 3, that's equal to the square root of 9, or just 3. You can use these properties of radicals to write expressions in simplified form. So if I'm simplifying radical expressions, we want to make sure the following conditions are met. The index n is as small as possible. The radicand contains no factors other than 1 that are nth powers of an integer or polynomial. The radicand contains no fractions, and no radicals appear in a denominator. To eliminate radicals from a denominator or fractions from a radicand, you can use the process called rationalizing the denominator. To rationalize a denominator, multiply the numerator and denominator by a quantity so that the radicand has an exact root. So let's study some examples. So let's simplify this expression. I have the square root of x to the 4th over y to the 5th. So again, if I take it and I use the quotient property for radicals, right, this would be the same as the square root of x to the 4th over the square root of y to the 5th, right? These are equivalent to each other. And I know that x to the 4th, if I turn that into a perfect square, that's just x squared squared. Y to the 5th would be equivalent to y squared squared, because that's y to the 4th, times y. And now I have my perfect squareds here that I can simplify. So when I square root a perfect square, that's just going to leave me with x squared. If I square root a perfect square down here, that's going to leave me with y squared. And since that is not a perfect square, that stays in the radical. So it's just going to be x squared over y squared radical y. But if you notice, I did go through the simplification process, but I have a radical in the denominator. So I need to rationalize the denominator. Well, how do you rationalize the denominator? You have to multiply by that exact same radical, right? Because I want it to be a perfect square. If I do the square root of y times the square root of y, that will give me y. But in order to do this, I have to multiply by the denominator and the numerator by the same thing. Hence why I'm multiplying by square root of y over square root of y. So when I simplify that, right, y times y, or square root of y times square root of y is y, so that's going to give me y to the 3rd down here. And then in the numerator, I'd have x squared times the square root of y, right? Square root of y times square root of y gave me y down here, hence where I get the y to the 3rd. Oops, sorry. So this would be our final simplified answer there, right? We got rid of all the radicals in the bottom. All the radicals have been simplified. This is the only one that's left because there's nothing left to do. Let's look at the next one. So here it's asking me to simplify this expression. So I have the 5th root of 5 over 4a. So I'm going to go ahead and look at it. So again, I'm going to do the 5th root of each one, right? So the 5th root of 5, the 5th root of 4a. So again, in order to rationalize it, I have to make sure I create the perfect fifth root before I had, since it was a square root, I was trying to create perfect squares. So in order to get rid of this radical, I need to have something that would be a perfect fifth root. And I know 4 times 8 is going to give me 32, and 32 is a perfect fifth root. And a times a to the fourth is going to give me a to the fifth because it's another perfect fifth root. So again, the numerator and the denominator have to multiply by the same thing. So I'm going to use my product property there. And then, so when I multiply these out, 5 times a to the fourth is 40, a to the fourth. And in the denominator, 4a times a to the fourth, 4 times 8 is 32, a times a to the fourth is a to the fifth. So again, perfect fifth roots there. So the fifth root of 32 is 2. The fifth root of a to the fifth is a. And in the top, that would be my simplified answer. I can't, there's no perfect fifth roots to simplify there. So what about operations of the radicals? You can use the product and quotient properties to multiply and divide some radicals respectively. So here, let's multiply these radicals together. So again, I'm going to look at that. And again, I can use the properties that we know how to multiply with. So I know I can multiply 6 times 3, and I know I can multiply the third root of 9n squared times the third root of 24n, right? So these get multiplied together here. And that's going to give me 18, and then it's going to be the third root of, well, I have 2 to the third power, right? 3 to the third power, and n to the third power, because I know 9 is 3 times 3, and then 24 is 8 times 3, so that's 3 factors of 3 there, and then 8 is 3 factors of 2, and so then I can simplify that, right? Because those are all third roots, perfect third roots. So that's going to give me 2, that's going to give me 3, and that's going to give me n. So then I would do 18 times 2 times 3, which is 108 times n, 108n. So now the question is, can you add radicals just like we would in the same way we would multiply them? In other words, if radical a times radical a equals radical a times a, does radical a plus radical a equal radical a plus a? Well, the simple answer is you cannot add radicals in the same manner as you multiply them. You add radicals in the same manner as adding monomials or adding like terms together. So that is, you can add only like terms or like radicals, right? So the same way that we would add things that have variables together. All right. So, like if I have radical 3 or square root of 3 and cube root of 3, these are not like expressions, right? These are not like terms. So I could not add those together. If I had the fourth root of 5x and the fourth root of 5, again, these are not like expressions. And if I had 2 times the fourth root of 3a and 5 times the fourth root of 3a, these are like expressions. So these I could combine together. So let's take a look at a problem here. So here they want us to simplify 2 radical 12 minus 3 radical 27 plus 2 radical 48. So again, I know I have different radicals here, but I can simplify those radicals. 12 can be simplified into 2 squared times 3, right? And 27 can be simplified into 3 squared times 3. And 48 can be 2 squared times 2 squared times 3, right? Breaking them apart, or factoring them apart from each other. So when I simplify them, that's going to be a perfect square there. That's a perfect square there. Perfect square there and there. And so then when I simplify them, if you notice, I am left with a radical 3 there, radical 3 there, radical 3 there, and then 2 times 2 is 4, 3 times 3 is 9, 2 times 2 times 2 is 8. And so now when you simplify it, you can see that they all have the exact same radicals there. So they're all radical 3. So 4 radical 3 minus 9 radical 3 plus 8 radical 3, those are like terms. So when I combine them, they'd be 3, because 4 minus 9 plus 8 would give me 3. So it's 3 radical 3. It's kind of like combining like terms when we have variables. Let's look. Just as you can add and subtract radicals like monomials, you can multiply radicals using the FOIL method as well. So let's look at these. So here I have 3 radical 5 minus 2 radical 3 times 2 plus 1 radical 3. So let's go ahead and take a look at this one. If I use the FOIL method, right, I would do first terms times outside terms times inside terms times last terms. And so this would be, if I FOILed it out, I would multiply these together. So 3 radical 5 times 2 plus 3 radical 5 times radical 3 minus 2 radical 3 times 2 minus 2 radical 3 times radical 3. So if I multiply them out, 2 times 3 is 6 radical 5, and then I would have 3 times radical 5 times radical 3. So the radicals get multiplied together, so that's going to be radical 15. Again, 2 times 2 is 4, so that's 4 radical 3. And then here I'd have 2 times radical 3 times radical 3. And I know radical 3 times radical 3 is radical 3 squared, or the square root of 9, or just 3. And so when I simplify them, this is where I'm at. I'd have 6 radical 5 plus 3 radical 15 plus 4 radical 3 minus 6. And then the same thing in the other one, I'm going to go ahead and FOIL it out. And then that would leave me with 5 radical 3 times 5 radical 3 plus 5 radical 3 times 6 minus 6 times 5 radical 3 minus 6 times 6. So now I go ahead and simplify it. So again, radical 3 times radical 3 is 3 squared. And then 5 times 6 is 30, so it's 30 radical 3. And this one I would do 6 times 5, so again I have 30 radical 3. And then 6 times 6 is 36. Now, one thing you want to recognize is, if you notice this one in the middle, it's if I add 30 radical 3 and subtract 30 radical 3, those will zero out. They are like terms. You can combine them. I know the square root of 3 squared is just going to give me 3. So 3 times 25 is 75. These zeroed out, minus 36. So the last part here is just to simplify that. 75 minus 36 is 39. So that's how you would simplify by using the FOIL method with expressions that have radicals. So binomials, like those in example 5b, of the form a radical b plus c radical d, and a radical b minus c radical d, where a, b, c, and d are all rational numbers, are called conjugates of each other. The product of conjugates is always a rational number. You can use conjugates to rationalize denominators. So here's an example. So here I have 1 minus radical 3 over 5 plus radical 3. Now the conjugate, if I wanted to rationalize this denominator, I would want to get rid of this radical, and I can't do it by just multiplying by radical 3, because then I would end up having a radical over here. So what we do is we would use this thing called a conjugate, and the conjugate is essentially the same exact expression, but instead of the addition, you're going to have the subtraction. So let's take a look at that. So if I wanted to rationalize this denominator, I would multiply it by its conjugate, which would be 5 minus radical 3, right? Now these are conjugates of each other, but I got to multiply the numerator and the denominator by the same thing. Okay, so when I do that, now I can use the FOIL method in both the top and bottom. So when I multiply the top, it's 1 times 5, 1 times negative radical 3, negative radical 3 times 5, and then negative radical 3 times negative radical 3 is positive radical 3 squared. In the denominator, I would have 5 times 5, which is 5 squared, 5 times negative radical 5, which is negative 5 radical 3, positive radical 3 times 5, which is plus 5 radical 3, and then radical 3 times negative radical 3, which is negative radical 3 squared. So again, remember that the conjugates of each other will eliminate that middle term. And so it's just going to leave me with 5 squared minus radical 3 squared. And so when I simplify that, that's just going to give me 25 minus 3 in the denominator, which is 22. And on top, I'd have 5 minus 1 radical 3 minus 5 radical 3. Those are like terms, so that's why you get minus 6 radical 3. And I know that 5 plus 3 is 8, so those would be combined as like terms as well. And so here we're almost done. If you notice these 3 numbers here, right? This fraction can actually be simplified because you notice with the coefficient there, 8, 6, and 22 are all divisible by 2. So if I divided everything by 2, it would be 4 minus 3 radical 3 over 11, because 4, 3, and 11 are what you would get if you took 8, 6, and 22 and divided it all by 2. So that's how you would use a conjugate to rationalize the denominator. Thank you guys for watching. Let me know if you have questions.